So, NASA just tested a brand new kind of rocket engine. It's an idea that's been kicking around for, well, centuries, but it's always been just out of reach. And today we're going to break down how this revolutionary design could completely change the future of space travel by taming the one thing that engineers used to fear the most. And really, the whole thing boils down to this one wild idea. What if a rocket's greatest enemy, a destructive force that engineers spent decades trying to stop, was actually its greatest strength waiting to be unlocked?
So, what's the big breakthrough here? Well, this new engine promises to improve fuel efficiency by up to 5%. Now, I know what you're thinking. Just 5%? Is that it? But in the world of rocketry, that is not a small tweak.
Yeah, I know. 5% doesn't sound like a lot, but in this game, it is a monumental leap forward. You have to remember, when you're trying to escape Earth's gravity, fuel isn't just part of the equation, it's pretty much the entire equation. So let's put that 5% into perspective. For a monster rocket like the Saturn V that took us to the moon, a 5% fuel saving would be 103 tons. To give you a sense of scale, that's basically the entire dry weight of a modern Falcon 9 rocket. Yeah, the whole thing. This isn't just about saving a bit of cash. It's about fundamentally changing what's possible, letting us launch way bigger payloads way farther out into the solar system. Okay, so how on earth does this thing work? Well, the secret lies in harnessing a supersonic blast, and it uses a principle that completely flips a century of engine design on its head. All right, to really get this, we need to talk about two very different ways to burn something. See, virtually every rocket ever built uses something called deflagration. Think of it like the flame on your gas stove. It's a fast burn, but it's predictable, subsonic. This new engine, a rotating detonation engine, or RDE, uses detonation, and that is a whole different beast. It's not a burn, it's an instantaneous supersonic explosion that rips through the fuel faster than the speed of sound. So instead of a steady burn like a normal engine, an RDE does something way, way cooler. It basically creates a single, continuous explosion that just keeps going. First, fuel and oxidizer get pumped into this ring-shaped chamber. Then, a single spark kicks the whole thing off, creating a supersonic detonation wave. And here's the magic. That wave just travels around and around the ring at insane speeds. We're talking Mach 3 to Mach 6, sustaining itself. All those expanding gases have nowhere to go but out the back, creating this incredibly powerful and constant thrust from a never-ending explosion. But here's the crazy part. To really get why this is such a huge deal, you have to look back in time. Because for over 100 years, detonation wasn't something to be harnessed. It was the enemy. I mean, for the last century, the entire goal of rocket engineering was to prevent detonations at all costs. They even gave them this tame-sounding name, combustion instabilities, to sort of downplay how violent they were. But don't be fooled. These things were unpredictable, destructive forces that could literally tear a rocket engine to shreds in the blink of an eye. And there's no better example of this fight than with the Apollo program's F1 engine. This was the most powerful single-chamber rocket engine ever built, and it was a nightmare to get working. After catastrophic failure back in '62 completely obliterated an engine on the test stand, it took years of work, chasing down more than a dozen different potential causes just to figure out what was going on. Honestly, baiting these instabilities was probably the single biggest engineering challenge of getting us to the moon. And get this, the way they tested their fixes was just insane. To make sure their solution, which involved putting these things called baffles inside the engine, would actually work, they literally set off small, controlled bombs inside a running F1 engine on the test stand. They had to create a mini detonation on purpose just to see if they could stop a bigger one from happening on its own. Wild. So after all that, you've got to be asking, why on earth would anyone want to play with this fire? The answer is pure, simple efficiency. You see, a standard gas turbine engine, say running on hydrogen, might top out around 37% thermodynamic efficiency. A detonation engine, though, we're talking a theoretical efficiency of almost 60%. That's a massive, massive jump in how much energy you can squeeze out of your fuel. The prize was just too big to ignore. So for decades, that huge prize was just sitting there, totally out of reach. What changed? What finally gave us the keys to control this thing? Well, the first big key is all about materials science. To survive a continuous explosion, you need some seriously exotic stuff. Enter GRC-COP42, a superalloy developed by NASA.
This stuff is incredible. It can take the insane heat, but it's also amazing at pulling that heat away from the most critical spots. And crucially, it's designed to be 3D printed.
And that 3D printing part is key number 2. It lets engineers create parts that were literally impossible to make before, like something called a fluid diode. It's basically a valve with 0 moving parts. Think about that. Its incredibly complex internal shape lets fuel flow in easily, but the instant that supersonic pressure wave tries to push back into the fuel line, the flow basically crashes into itself and blocks the path. You just can't machine a part like that. It has to be printed.
And finally, the design brings back a classic, super cool idea, the aerospike nozzle. You can think of it as an inside-out rocket bell. What makes it perfect for an RDE is that it automatically adjusts its own performance based on the outside air pressure. But more importantly, it's also great at handling the constantly fluctuating pressure coming from that detonation wave circling inside the engine.
Okay, so we've got the new materials, we've got the advanced manufacturing. Where does that leave us? What's the future of detonation actually look like? The great news is this isn't just on a blackboard somewhere. We're seeing real, tangible progress. Back in 2021, JAXA, Japan's space agency, actually tested one of these in space for about 6 seconds. And then in 2023, NASA ran their engine for almost 2 full minutes, proving the materials could take the punishment and, crucially, that they could shut it down and start it back up again. But, and this is a really important but, we're not there yet, not by a long shot. This whole process is fundamentally chaotic. Engineers are still trying to figure out how to keep that detonation wave perfectly stable, how to control a system that wants to be uncontrollable, and how to scale this whole thing up for much longer burns and way, way more thrust. It really leaves you with an incredible thought, doesn't it? The very same chaotic, destructive force that almost kept humanity from reaching the moon in the first place. Could it now be the key that finally takes us far, far beyond it?